Hello students, let us start our next topic, that is isomerism in coordination compounds. So we have seen in previous class the definition of the coordination chemistry and how the complex ions is relating to coordination chemistry and the basic terms of the coordination chemistry, ligands, and also we have seen the nomenclature of the coordination chemistry, right? So now let us see here isomerism in coordination chemistry. So what is isomerism? Isomerism is nothing but what here? The isomerism is nothing but here the atoms or molecules having same formula with different arrangement. We call it as isomerism. This isomerism in coordination compounds divided into two types. Mainly it is divided into, so means what we can say here, one is structural isomerism, another one is stereoisomerism. So what we can say here, it is divided into two isomers, that is what here, structural isomers and stereoisomer. What is structural isomers? Structural isomers means what here, the atoms, ions, molecules having different structures. We call it as what here, structural isomerism. Okay, this structural isomerism again divided into 6 types. That is what here, ionization isomerism, hydrate isomerism, coordination position isomerism, linkage and polymerization. So these are the 6 types of the structural isomerism coming to coordination chemistry. But coming to inorganic chemistry, what we speak there, we are going to speak about structural, functional, position, chain, metamerism, tautomerization. So these all will come under structural isomerism in organic chemistry. But coming to inorganic chemistry, that is about mainly coordination chemistry, what we can say here, it consists of 6 types, that is ionization, hydrate, coordination position, linkage and polymerization. And let us now see the second type, that is stereoisomerism. The stereoisomerism is nothing but what here, stereoisomers mainly depends upon 3D dimensional structures, we can say. Means we can say spatial arrangement. Okay, we have seen coordination polyhedron. The space to the spatial arrangement, the ligands are directly attacking. That one we call it as what here, coordination polyhedron. So coming to here, stereoisomerism. Stereoisomerism is nothing but what here, atoms having same formula but different spatial arrangement. That one we call it as what here, stereoisomerism. This stereoisomerism is again divided into 2 types, that is geometrical isomerism and another one is optical isomerism. Geometrical isomerism is nothing but what here, ligands having different spatial arrangement. Means what here, the ligand should be arranged differently. That one we to the central metal atom. That one we call it as geometrical. And coming to optical, what we can say, which are non-superimposable mirror images. Means what here, mainly enantiomers, chiral compounds, asymmetric compounds. We call it as optical isomers. Okay, I think you have clear idea about isomers. This is the brief introduction of the isomerism. So now let us see isomers having same molecular formula, that but their atoms are arranged either in a different order. Atoms, that one we call it as structural. With spatial arrangements we call it as stereoisomers. Okay, so what we can say here, sorry for the disturbance. So isomers having the same molecular formula but they're different arranged atoms in different order, we call it as structural, and spatial arrangement we call it as stereoisomers. Now let us enter into one by one. So structural isomer, in this we are having first one is ionization isomerism. What is ionization isomerism? In this type of isomerism, the difference arises from position. Ionization means what? Exchange of ions. Simple, I am saying exchange of ions, we call it as ionization isomerism. So coming to definition here, for example here, the difference arises from the position of grips within or outside the coordination sphere. outside the bracket or inside the bracket. The ions is going to exchange. That one we call it as what here? Ionization. Means they give different ions in solution. Okay, when you dissolve in water, they give different solutions. For example, here we have taken COBrNH3 5SO4 one molecule and another one COSO4 NH3 5Br molecule. So coming to here, the Br is inside, SO4 is outside. When you dissolve it in water, what happens? It is dividing it into COBr NH3 5 plus and which is a SO4 2 minus, which gives red violet. Okay, after that what happens? This molecule also, when you dissolve it, what happening? So this SO4 will come inside, this Br minus goes outside, which is a red color. So means what? Exchange of ions. So what I'm saying, ionization isomerism is what here? The molecular formula is same, but there is exchanging the ions. That one we call it as ionization isomerism. So here the Br is inside, SO4 is outside. When you dissolve it in water, what happening? The Br came outside and SO4 came inside. So this is nothing but ionization isomerism. This is one of the example, another example they have given. Okay. So let us see next one, hydrate isomerism. So hydrate isomerism is nothing but what? In the name itself it is representing. Hydrate is nothing but water molecules. So the water molecule is replacing with the another ligand. We call it as hydrate isomerism. Means what here? The replacement of water by another molecule. We call it as hydrate isomerism. We are having different types of isomerism, that is CrH2O6Cl3 one isomer. Another one, when it is replacing with water molecule, what happens? The Cl will come inside and water molecule go outside. That is the molecule we are getting. And if you replace another Cl, we are getting, this is the molecule. I think clear about this. Means what happens? In the first example, what happens? H2O6 we are having. In second example, what happening? The one water molecule is replacing with chlorine atom, coordinating with chlorine atom. And third step, what happening? Another water molecule is coordinating with another chlorine atom. Means what here? The replacement of water molecule by another ligand. That one we call it as what here? Hydration isomerism. Okay. So this is nothing but what here? Structural isomerism. And third one, we are having linkage here. Linkage isomerism. Linkage isomerism is nothing but what here? The isomer complexes in which ligands can coordinate with the central methyl atom with two or more atoms. So as we have seen, ambidentate ligand. Ambidentate ligand is similar to the linkage isomerism. Example, if you have been taking MnO2. Okay, so or simply we can take here CN, cyanide. Okay, so here what happens? This is one of the example I have taken. When you dissolve it in water, when you dissolve it in solution, so it is going to represent with M and C. So here the position is changing, the molecular formula is same, but the atoms are changing. Means what? It is linking with other atoms. So C, first molecule, it is coordinating with carbon, and in second molecule it is coordinating with nitrogen. Means it is forming as a cyanide. When you dissolving it in water, what happens? Isocyanate. So this is nothing but what here? Linkage isomerism. How these ligands are interrelating. Means two atoms, with the two atoms it is going to interrelate with each other. That one we call it as what here? Linkage isomerism. Having this is about the linkage isomerism. See here they have taken the example CONH34NO2ClCl, and here the ONOClCl. Okay, so means what here? The nitro group is going to linkage. Okay, for in the first molecule if you are getting cyanide, in the second molecule we are taking NC. Here also OCN or NCO we can say. Here also CNS we can take or NCNS. Okay, so this is the molecule we are going to exchange. So this is about linkage. Next one, let us see coordination isomerism. So what is next one here? Coordination position isomerism. Coordination position isomerism is nothing but mainly we are going to take polynuclear complexes, we can say. Polynuclear complexes is nothing but what? More than 2. We call it as polynuclear. So here the interchanging of ligand between metal atom and also complex, that one we call it as what here? Polynuclear. See in this example here we are having NH3 4 NH3 twice Cl2. Okay, so coordination positions will change here mainly. So what happens, this one nitrogen atom is replaced here, one chlorine atom is replaced here, means what, this chlorine is coming here and one of the NH3 is going here. So means what here, this is a unsymmetrical which is not in same direction, and after exchanging of the ligands what happens here, there is a symmetrical, means what, the positions isn't same, means what we can say here, when you dissolve in water molecule, when you exchange the ligands, it should be in a same molecule, that one we call it as coordination position isomerism. When you take the first compound, it is unsymmetrical. Afterwards what happens, when you take, after exchanging the ligands, it is changing the position, that is what here, symmetrical ligand. This is nothing but coordination position isomerism. Next one, if you have been seen, coordination isomerism. Coordination isomerism is nothing but what here, both cation and anion of a complex compound is a complex, means whether it is a cation, whether it is a anion. So this is a cation, this is a anion, it is a complex. So their exchange of ligands between two coordination pairs, means what happens, these ligands are going to exchange, that one we call it as what here, coordination isomerism. Here the molecular formula will be same, but what happens here, the metal atoms can exchange and also the ligands can exchange. Here the ligands is exchanging, first step. In the second step what happening, the metal atoms are exchanging, that's why we call it as what here, coordination isomerism. So these are nothing but 6 types of structural isomerisms. What is the first one? Ionization. Second one, hydration, linkage, coordination position and coordination isomerism, and then ligand isomerism we are going to have. So this is nothing but the structural isomerism. Now let us enter into geometrical isomerism, which is a stereoisomerism. Okay. So see here, what is stereoisomerism? The atoms, the different atoms or molecules should be arranged in a, means the ligand should be arranged in a spatial arrangement. We call it as what is stereoisomerism. Now if you have been seen here, the isomerism consists of 2 types. One is geometrical isomerism, another one is optical isomerism. Geometrical isomerism is nothing but what here, this mainly depends upon ligand which occupy different positions around the central metal atom. That one we call it a geometrical isomerism. The geometrical isomerism takes place under coordination number 4 and 6. Okay, if you are having 4 is the coordination number. For example, if you have been taking CH4, okay, that one represents tetrahedral. In the same way, geometrical isomerism consists of here tetrahedral square planar complexes and octahedral complex. If you are having coordination number 4, it is a tetrahedral and square planar. If you are having coordination number 6, that is a octahedral complexes. In this mainly it consists of 2 types. One is cis form, another one is trans form. Cis form is nothing but what here, the ligands if it is in same side, means side by side if you are having adjacent to each other, that one we call it as cis. If it is opposite, that one we call it as trans. Now let us see about coordination number 4. Coordination number 4, what I have told you, it consists of tetrahedral and also square planar complexes. In tetrahedral complexes what happens here, cis trans isomerism is not possible. Why? Because here the 4 ligands are adjacent to each other. So if you have been seen here cis and trans, so means in complex we are having different types of examples. For example, CH4 if you have been taken, the hydrogens is in all 4 hydrogens are same. In the same way, if you take CONH3 here also nitrogen atoms is in same. Means what happening here, if you are taking coordination number 4 in tetrahedral complexes, all molecules, all ligands is in same, means they are also arranged in same position. It will not represent cis position and trans position. In coordination compounds, in geometrical isomerism, the tetrahedral complexes is not possible. Why? Because the 4 ligands are arranging symmetrically. And coming to square planar complexes. In square planar complexes, what happens? Here, these are going to arrange differently. Example, if you have been seen here. This is the example if you seen here, PtCl to NH3, which is a square planar complex. The structure of this one is this. Okay. So coming to here, the square planar complexes which will represent, means what here we are having different types. Here one of the example we have taken what here, Ma to B2. Ma is nothing but central metal atom, A is nothing but 2 ligands, B is nothing but 2 ligands. One of the example we have taken, that is PdNO2 twice, NH3 twice, and PtCl2 Py2. Okay, so in cis form what happens? 2 molecules should be in adjacent side. In trans forms what happens? It should be in opposite sides. Okay, so this is nothing but first compound. And coming to second one, we have seen the first example Ma to B2, and the second one we are having Ma to BC, means what, there are cis and trans isomers depending upon A group which are adjacent and opposite to each other. Example, we have taken Pt Py2 and H3Cl. So means what happened? Py is in cis position and these two different atoms, but these two atoms are in cis position, no? That's why it is a cis. And coming to here, the pyridine is going to change the position. This one is a trans. And next example, if you have been seen, MABCD, 4 groups are different. Okay, so if here how we are going to take the structures of fixing the position of one ligand, say A, and by placing other ligand B, C and D. So it is having total 3 isomers. So when you change the positions, one position is this one, another if you change NO to NH2OH, okay, PY NH3, another position. So it represents just normally the positions only. It can't represent the geometrical isomerism. Next, coming to here, coordination complexes 6. 6, it consists of 2 types of examples here. 6 is nothing but what here, octahedral geometry it will show, and also this octahedral geometry also exhibit geometrical isomerism. So some of the complexes like Ma6, Ma5b will not show geometrical isomerism. Why? Because the compounds is in same direction. So here we are having different types of examples, that is Ma4b2, Ma2b4 or Ma4bc. So these type of examples will show the octahedral complex. So this is the octahedral complex we are seeing, which is in a cis position, we can say here. Why? Because the 4 NH3 is in same position. When you change the position, the chlorine atoms, so here what happening, the trans position we are getting. Okay, so this is nothing but cis and trans. So if you take geometrical isomerism of the type this one, these are different examples. So here the pyridine, all 3 in same direction, cis, all 3 in same direction, cis. So here coming to trans, what happens, the Cl minus which is in opposite direction, this is in opposite direction, this is in opposite direction. That's why it is what here, trans position. And octahedral complex, we have been seen different examples. Sorry. We are having different types, that is MABCDEF. So means what, all ligands are, means total 15 geometrical forms we are going to get, that is here. Only out of these 15, only 3 are possible of this compound. And coming to here also we are having bidentate ligands. They can also show geometrical isomerism. They may be same or different. Okay, so here example COEN2Cl2 plus we are going to take here. So this is the geometrical isomerism, COEN2 Cl6 Ma2b2. So which is in same direction cis, which is in opposite direction, it is a trans. When you take it in pyridine, if you take the En is in same direction, that is cis. If the En is in opposite direction, that is a trans. And next one is optical isomerism. Optical isomerism is nothing but what here? Non-superimposable mirror images, we can say. What is optical isomerism? In this mainly we required monochromatic light, polychromatic light. Okay, so plain polarized light, we can say. What is plain polarized light? So to the light source, if you take a light source, so here mainly we can say these are enantiomers, we can say. Why? Because enantiomers is nothing but what here, which are non-superimposable mirror images, we call it as optical isomers, and this will be having no plane of symmetry. That one we call it as chiral molecule. So for example, if you take your hand and place it up mirror, what happens? Opposite of your hand it will show. Means what here? It is nothing but optical isomerism. So if 4 different groups are attached, which cause here chiral center or asymmetric carbon atom, that one we call it as what here? Symmetric carbon atom. The molecules with a plane of symmetry, we call it as ecchiral, and here we are having only chiral molecules have optical isomers. Okay, for example here, so simple substances which show optical isomerism, that one we call it as what here? Enantiomers. So due to plane of polarization, means the substance which is taking under the light, that one we call it as plane of polarization. If it is in a clockwise direction, we call it as levo form and dextro form. Okay, if it is in anti-clockwise direction, it is a dextro form. If the solution are equally concentrated, then 2 isomers are same. That one we call it as what here? Racemic mixture. In the stereochemistry we are going to learn these are the basics. Okay, now let us see here. This is a unpolarized light. To a nickel prism we are placing, it is divided into polarizer, analyzer. So this is a slit which will be taking into same direction. If we are getting different directions, it will be passing only same direction. This is the substance. Okay, so this substance, what happens to our eye? If it is rotating towards right, that one we call it as dextro. If it is rotating towards left, that one we call it as levo. Okay, if one enantiomer of a chiral compound, means what here? If one compound is going to place in a polarimeter and polarize light, okay, the plane of polarization will rotate. Means how much it will rotate here? 32 degrees to the right, other will rotate to 32 degrees on the left. This is nothing but optical activity introduction. So this optical activity, metal complexes not having any element of symmetry, means plane of symmetry, center of symmetry, this will show optical isomerism, which will have dextro and levo form. So in geometrical isomerism, what we have discussed, tetrahedral complexes is not possible. But coming to here, optical isomerism, tetrahedral complex is possible, which will show optical isomerism, okay, which contains symmetrical ligands. These all will consist of optically active compounds. Example here we have given. See here, one is MEPH, another one is MEPH. So coming to here, when you place it in a mirror, what happens? This molecule will exchange, it will rotate. Okay, opposite to this one, that one we call it as what here? Optical isomerism. And for square planar complexes, if you have been seen, so here PHH, PHH, ME, ME. Here also it is showing, these are also optically active, we can say, because all the metal atoms and ligands is in the same plane. The molecules also having plane of symmetry, and it cannot exhibit optical isomerism. Why? Because the platinum which is having, it is forming into 2 forms. One is +2 form, another one is +4. Okay, so this is nothing but square planar complexes. Next one, with coordination number 6 means what here? Octahedral complexes. We are having bidentate, tridentate, polydentate. Here example we have taken COEN3, Cl3, okay, and COOX3, Cl3. So these all molecules is going to exhibit the optical isomerism, which is in same side, this is in opposite side. One is in dextro form, this is dextro form, this is L form. Okay, when you place a mirror, if it is representing two forms, that one we call it as optical isomerism. Here we are having different types of examples. See here, so this is dextro and this is levo form, and this is also cis, and trans is nothing but, cis is nothing but same, trans is opposite. Means what happens here, dextro and levo forms. And coming to here, this is asymmetric form, and also inactive compound it is going to show. These are the examples of different types of examples we are having here with the NH3Cl2En. When you rotate this one, it is coming this side. This is D form and this is L form. So this is one of the example which is containing hexadentate ligand. So this is a L form and D form. Okay, unidentate ligand also we are having. So this is nothing but optical isomerism. In the next class we can see the different types of bondings. Thank you.